Hi folks, this is Laura Chappell, and together with Ginny Spicer, I'm going to be taking you through the Licklider Transmission Protocol, or LTP, which was originally designed for space communications. I know that sounds really boring, so maybe it would be better to name this presentation Ground Control to Major Licklider. This is an image of Joseph Carl Robnet Licklider, and you can look up information about him online, but essentially in 1962 he wrote this great memo about intergalactic communications. Obviously this guy could see into the future. So this protocol was named for him. Let's begin with just the LTP essentials. So LTP provides retransmission-based reliability, and this is really strange because guess what? I'm going to be showing you this communication running over UDP, not TCP. So normally when we think about reliable communications and retransmissions and things, we think about having TCP as a transport layer protocol. But in this case, LTP is actually going to sit on top of UDP. And LTP is ideal for links that have a very large round-trip time, or they have complete interruptions in their communications. LTP is documented in RFC 5326 and also the Consultative Committee for Space Data Systems Blue Book 734.1-B-1. Oh, the reason why I had that shark on that last slide, I should mention, is because we're going to go into Wireshark and we're going to analyze some LTP communications in here. And separately, we have a video where Ginny's going to take you through a Wireshark challenge and have you open up an LTP trace file in Wireshark and answer some questions about that communication. So back to this idea of large round-trip times. If we look at the round-trip times between Earth and Mars, that round-trip time can range between 6 and 40 minutes round-trip time. So we've got definitely something a little higher than your typical internet-based round-trip times. So we're going to start with some key terminology here. So I have several sets of key terms. The first one here is client service instance, and you can think of that as the application that is using LTP to transfer data. So let's say on the left-hand side of this slide, I have a console here, and you've got a ground control system that is communicating with the International Space Station. Okay, it's the application software running at the ground control station that would have a client service ID number on it, and it would communicate with the application that is up running on a computer system up in the International Space Station. Those applications use the LTP engine. So we have LTP engine communicating with LTP engine. A block is a bunch of data that's coming down from the application to the LTP engine and being sent from one peer to the other peer. Now, typically what's coming down is going to be the bundle protocol. We have a separate video on analyzing the bundle protocol over TCP. A session is just generally the activity between two LTP peers that are exchanging a block. And this is going to be really strange when we start looking at the traffic. The way a session is different than a UDP conversation. Sessions are unidirectional, which means that if at that command station, that control panel, if it's communicating with the International Space Station and it opens up port 55216 to communicate to UDP port 2112, let's say, it will send its data across that port, but it wants to get let's say, a report back to see, did you receive this information? That report is going to come back on a different set of UDP port numbers, and Wireshark will see it as a different conversation. It's the same session, but it's a different UDP conversation. You can have multiple client service instances running on top of an LTP engine. So each one of these purple ovals here would represent a different application. Below that, you would have the LTP engine at each side of the communication. This is your data transmission procedures using LTP underneath. You have a client service ID number also identifying the application up above, and you have an engine ID number on each side as well. And then below that we have UCP, or the underlying communication protocols, and that may be RF frequency, radio frequency. Who knows? We're doing all this work with experimenting with laser comms. So whatever that underlying communication protocol is. In this example coming up, I'm going to use this idea of a command station on Earth talking to the International Space Station. The command station would have the LTP client software and engine, and the International Space Station would have a computer system with the LTP client software and LTP engine software as well. The way that I'm going to show it to you is based on what you will see out of the CCSDS Blue Book. And we're just going to build on this as we go through this presentation. But on the left-hand side, I have my command station down on Earth, my control console with the LTP client and the engine running. And then up on the International Space Station, I have the LTP engine with the LTP client, the application software basically. A block will be sent from the application to the engine, and each one of these blocks is numbered. And you'll see this inside of the LTP header. So for example, let's say we send down a block to the LTP engine and we say this is session number 3. All right, so that goes down to the LTP engine, and the LTP engine is going to send packets to the target LTP engine. And in each one of these packets that goes out to the target, it will define that this packet is part of session 3. So you'll see that session numbering inside of the headers. The receiving LTP engine will pass this data then for that session up to the LTP client software, which would be the application on the receiving end. Here's something that's really interesting about LTP communications. Data is either colored red or it's colored green. Any data that is considered red data is transmitted reliably, and the receiving end will track the offset of the data and the data length for the incoming packets. And when we ask for a report back from that receiver should tell us which one of the offsets and lengths it has received, so we can figure out what needs to be retransmitted. Any data that is labeled as green data is transmitted unreliably, and if a packet goes missing and it's been marked as green data, we will not recover that packet. That data is gone. At the bottom of this slide, you'll see that I have a session block here on the left-hand side, and it has both red and green data because a single session can carry both data types. The red data type goes first, the green data type goes next. Let's say you lose a couple of packets when transmitting the red data type. We are going to go through the process of retransmitting those. But if you lose something in the green part, it's not going to be retransmitted. And then before we go and look at some of this communication, we have to get this other term. We need to be familiar with this other term, which is the idea of an end of block. Now, an end of block can be used in a data communication that's only red data. It can be used at the end of communication that's only green data. And when you're sending both red and green data in a session, you'll see the end of block at the end of the green data, because red goes first, then green, and then the end of block will be defined as the last packet, on the last packet of that. So we have this same scenario, but this time we are sending green data. Now previously I just showed you sort of blue because I didn't want to talk about red and green yet. But now let's talk specifically about green data being sent across. So the application has data to send across. The application says you don't need to verify this data gets to the target. Therefore, this is going to be green data. So a block of green data, and this time we're on session number 1 here, gets sent to the LTP engine. That engine is going to start sending these green data packets, and you can see that we have an arrival indicator that goes to the application on the target side saying, hey, this green data packet came in. Or I should say this green data came in, because the packet isn't pushed all the way up, just the data is. Another packet goes across, and that green data is pushed up to the client. And then the third packet that goes across, it doesn't make it. Something happens, and it is dropped, destroyed, whatever. We're not going to recover that packet. Green data is sent across in an unreliable manner. It is not going to be retransmitted if it gets lost. Then we get another one that goes across and the data gets pushed up. And then the last packet that contains the last data segment of the block will have a marker on it saying end of block. And now we know we are done. So let's go look at a communication where we just have green data. And we do have packet loss, so we are not going to recover the packets that we've lost. And for this example, we're going to use our custom Wireshark profile. So Ginny Spicer is going to take you through the creation of our Wireshark custom LTP profile and explain to you what we did to create this profile that we'll be using for this session. So let's go out to that trace file. So I've opened up the trace file called LTP-green-1CONV, one conversation. Well, it's really one session here. We have one session between two hosts. We have one host, which is 0.0.0.3, and another host that's 0.0.0.2. Now, I should tell you that this trace file was captured using ION, which is the Interplanetary Overlay Network, or the communications testing system for interplanetary communications. When ION runs, it gives each address, or each host, the address of 127.0.0.1, the loopback address. So it gets very confusing to look at the trace file and see that traffic is going to and from the loopback address. Ginny and I went through and edited this trace file and the other trace files we'll share with you, so that we have different source and destination addresses in this area. The first thing you may notice when you open up an LTP trace file that you capture that way is that Wireshark may not recognize it as LTP traffic. We actually went inside of our profile and we forced the LTP dissector on a number of the different port numbers that we see in our ION traffic. In this communication, we have .3, which is sending data to .2, and .2 is echoing that data back. It is all the same session. Notice this is all done in the same session. However, they are listed as different UDP streams by Wireshark because the port numbers are different. This is what feels really weird, the idea that we are in a single communication session, but we are using multiple, two combinations, a set of different source and destination port numbers. We're so used to, you send a DNS packet out from port 5000 to port 53, you get the response back from port 53 to port 5000. That's not the way this works. We'll talk about that just a little bit later. But if we look at the first two packets, they're from .3 to .2. We can see that we've added a column for the offset and the length for the data portion in this packet. Offset 0, length 1191. The next data packet is offset 1191, and the length is 1190. Packet number 3 is the start of this echoing back process. In packet number 3, we can see that this is coming from 2 to 3, and the offset is 0 to 1191. And instead of the next packet being 1191 offset, it jumps to 2381, and it's actually the traffic going the other direction. This is the next time .2 talks. So we have packet loss that occurred right here already in the stream that's being echoed back. Wireshark on the right-hand side in the info column knows how to recognize that this is green data. And it knows that because when we open up one of these packets, we have the UDP header followed by the Licklider transmission protocol header, and here is that header. The LTP type field indicates that this is green data, but it is not an end of block packet. This is LTP type 4, and you can see that in the LTP type column here. Now, the column goes up and is displayed in hex format, whereas we see it in a decimal format down below in this field. It would be nice in Wireshark if we had a little consistency there, but I'm okay with it right now. So this trace file, we see that says on the right-hand side, green data reassembled in frame 110. Let's go all the way down to the bottom, and we can see frame number 110. Wireshark says, hey, it's green data. Notice that our LTP type value has changed to 7. Sure enough, there it is, LTP type 7, which means green data end of block. This is the end of dot 3 sending the data block to dot 2. The next packet is dot 2 sending the last data packet of the block back to dot 3. We can see that it's labeled green data end of block, and we have it right up here in this column. Unfortunately, on the right-hand side, we can see that Wireshark is having a little problem here. Unfinished LTP segment. Yeah, the LTP dissector at this time in Wireshark is not the strongest dissector in the world. The behavior, the normal, correct behavior of LTP is really throwing the Wireshark dissector for a loop here. It's trying to reconcile that we have segments of green data, and it doesn't make any sense to Wireshark. So don't worry about it. We know that the end of the block is the one that's marked as 7. There it is. And there's the echoed one. Here's some more key terminology. We've talked about this idea of red blocks and red data and green data. Well, we have these other designations that can be used on red data. We've already talked about end of block, and as I mentioned before, this end of block identifier can be put on red data. It can be put at the end of green data. And if you have both red and green data in a session, the red data will go first, the green data will go next, and the EOB or end of block will be at the end of the green data. Now, red data can also have a checkpoint value on it, indicating that I want to get a report back from my peer so that I know whether it's received all the data. This checkpoint is soliciting a reception report, soliciting a report from the target to see if everything's gotten there. Then there is another designation that we can have only on red data, and that is EORP, which is end of red part. And we see this when we have a session that includes red data and green data. We'll have a marker at the end of the red data part, an EORP, and it will also be flagged as a checkpoint as well. So we will see this coming up. This is going to feel weird when we start looking at this traffic, because you're going to see this unidirectional stuff, and we're so used to bidirectional communications over a single set of port numbers. So we're used to, especially in the Wireshark world, where we say, oh, add a stream column, or let's look at conversations. We're used to seeing something like this, where a request goes out from port, let's say 5190, request goes out to 53, maybe it's a DNS request here, a reply comes back, and Wireshark would mark this as a single stream or a single conversation. If we had, more information flowing back and forth, we have a request that goes out and we get, multiple packets of data, all of that would be marked as a separate stream or a separate conversation. Traffic flows bidirectional in TCP/IP communications. But when you get to LTP, traffic flows unidirectionally. And I do want to mention that the default port number for LTP over UDP is port 1113. Here's what you would see in LTP communications. You would see starting port number with red data in it going over to port number 3113. In Wireshark, we'd have to force a dissector for LTP on this traffic because it's not using the default port number. And that's okay. We just have to force the dissector on it. So we send red data over, red data, red data, and then at the end of the red data block, let's say that's all we're sending is red data, no green, we would mark this last packet of the block with an EOB, end of block. We would mark it with end of red part, and we would also mark it with checkpoint. And remember, checkpoint is our way of asking our peer that we're talking to send back a report on what is received. Once checkpoint gets sent across the network, a checkpoint timer begins. And if we don't receive that report back before the timer expires, we send another checkpoint packet over to the target system. When the report does come back, you'll notice that it will come back from a different set of port numbers. It's unidirectional on each pair of port numbers. So we can't receive data on port 56,624. We're sending data on that one. We can only receive stuff on a different port number. And so what you'll see in the trace file is a report coming back from a totally different set of port numbers. It just feels strange. Now we can see the report ACK going back with our original port pairing. Because it's flowing in the proper direction, everything's great. So it's a little bit strange because if we were to look at Wireshark's stream column that we added to our profile, this would tell us that there are two separate UDP streams or two separate TCP conversations. Well, yeah, it's really one session with two unidirectional flows in it. So you have to be careful when you're trying to filter out and look at one actual communication between, a console on Earth and the International Space Station. You really want to pull it based on the stream number, not the UDP stream index, or you want to grab it by the session number, excuse me, rather than by the UDP stream index number. So here's how a red data transmission would work. In this example, we have an application here, and the application is saying, okay, I'm going to set up session number 2. It's only red data. It's going to send that to the engine, the LTP engine. That engine is going to send that data out, and in every data packet, it's going to put in the offset of where this data sits within the block and the length, how many data bytes are in this packet. So here the first packet is offset 0, length 200. The next packet is offset 201 with length 200. The next packet going out is offset 401, length 200. And this is the end of my red data block. So it's marked as end of block, end of red part, and checkpoint. That checkpoint is asking the other side, did you get all of this data? Now, at this time, this data is then passed to the application on the target. We've asked for this report to come back, so we would expect to see a report coming back that says offset 0, length 601 in this claim area. And I'll show you these packets in a little bit here. And this indicates that from offset 0, 601 bytes were received by this target system, and the originator of the communication then sends the report ACK segment, say, hey, I got that report, thank you. Looks pretty easy, so let's go into a simple red data session. The trace file I'm going to open up now is called LTP-red-1conv-simple.pcapng. It's tough to get simpler than this. We have a single packet going across from 2 to dot 3, and it's just one data packet, offset 0, length 80 bytes. Dot 2 only has 80 bytes of data to send over to the target system. So this is the end of block, and we can see it down here in the type field. End of block, end of red part, checkpoint, and it's red data. So that's the value 03 in the LTP type field, or just 3 in decimal. 4 was green data going across. Now we are at red with checkpoint, end of red part, end of block going across. And Wireshark recognized that and says this is red data. Because that had the checkpoint value set, that triggers the report segment to come back from 3 to 2 to say, hey, I got that. And let's look at how it says I got that. In the report segment here, we've got the LTP header. The type field says this is a report segment, which means that right after that you'll see report segment. The report segment has a serial number and a checkpoint number. It has a report serial number and a checkpoint serial number. And notice that the checkpoint serial number for this report segment, right up here, matches the checkpoint serial number sent with that checkpoint packet up above. That's how we match a checkpoint, which is a request for a report, with the corresponding report. The report segment includes the report serial number, and the report ACK coming up in a moment will put in a report serial number so we can correlate a report with a report ACK. Now, here where we see it say upper bound, this is not to acknowledge receipt of everything up to the 80 bytes. Do not use upper bound and lower bound here to think that this is acknowledgement. No. The acknowledgement area is in the reception claims area down below. We see here it says reception claim count 1. Offset 0, length 80. When you start seeing offset 0 and length is all the way at the end, it's telling you, I got everything you sent to me. Let's look at the report ACK segment coming back. Report ACK segments, not very exciting. I'll go ahead and expand this out. There's our LTP header. We are now using type 9. And type 9 means report acknowledgement segment, and there's the report acknowledgement area. All it has in here is the report serial number to say, I am acknowledging the report you sent me that uses this report serial number. So that's how we correlate a report with a report ACK. Let's look at what the communication would be like if we have both red and green data in the session. So in this case, we're on session number 3. And we have red data, and remember that red data comes before green data. So the red data is going to be sent first, and then the green data. All of this is considered the block. So all of this is considered the block, not a red data block and a green data block. No. All of this is the block. So we know we're going to have an end of block marker at the end of the green data packets. So we've got red data going across. I'm not putting in the offsets and lengths and things like that. Another red data packet goes across, another red data packet goes across, and this is the end of the red part. And when you say end of red part, you have to have that checkpoint on as well. That red data is sent up to the application, and now that target system needs to send back the report segment saying, I got from offset 0 all the way up to whatever the highest count is, and the sender will send back the report ACK segment matching the report serial numbers. And then we have this green data that goes across. Now, we don't have to wait for the report segment to come back and things like that before we send the green segment. I did this in this slide so that I didn't have things overlapping with each other and getting really, really super ugly. So I wanted to show you the report segment, report ACK, and then show you what the green data would start to look like. So we have green data going across, and the last packet that goes across would be marked as end of block down here. So that is the end of this entire block. Let's go take a look at the LTP header structure. We're just going to go back into a trace file, and I'm going to take you into the header. I'm still in that LTP-red-1-conv-simple trace file, and I'm just going to look at this first packet here, which is a red data packet. The first field that we have in here is the LTP version field. The LTP version field is just a 4-bit field. Now in Wireshark, when we select a field here in the packet details window, Wireshark doesn't have the capability of only highlighting half of a byte down here, or 4 bits. So it'll always highlight the full byte, even though that's not correct. Okay, so it's only 4 bits long. After that, we have the LTP type field, the all-important LTP type field that says whether this is red data or it's green data, and is it a checkpoint, is it the end of the red part, is it an end of block. And this is also a 4-bit field. So 0 is the version number, which is the current version of LTP, and 3 is the type number. So we look down below in hex, we can see 0, 3, there you go. After that, we have a session ID field, and I'm going to expand this in Wireshark. You see the session originator, so 2 is a session originator. Don't get that confused with the IP address, they are different things. Then there is the session number, and again, in Wireshark, if you're trying to pull and look at one communication stream, series between one location and another, you want to pull them out based on the session number, not on the stream index number, because you can see these are different stream index numbers here. So this is session number 2, and even when somebody's talking over a different pair of port numbers, it's still in session number 2 here. There's the data segment. Now the data segment says what's coming up next. Here's our client service ID number, the bundle protocol. So typically what you'll find coming up after the LTP header will be the bundle protocol. That's basically what we would see as the application coming down, sending the block down to LTP. That's what's sitting on top of LTP. There's the offset of the data, offset 0, the length of the data, 80 bytes. Because checkpoint has been set up here, we have to provide the checkpoint serial number value. And again, that is how we match up the checkpoint with, or this checkpoint packet with the report that's coming back. Report serial number doesn't matter in this packet. We care about the report serial number in the report segment and the report ACK segment. And down at the bottom here we see data, and when we expand that we can see that there are 80 bytes in the data section. So the LTP header itself is static, but what follows it and what's added onto it will be different based on the purpose. So if I look down here at the report segment, I can see here's the LTP header, there's version, type, and then we have session originator, session number, header extension count, trailer extension count, and then what follows it is going to be dependent upon what LTP type number we see up above. This is not a data packet, so we don't see a reference to bundle. Instead, we see the report information. I've denoted that on this slide as well, this idea that you have this static LTP header, and whatever's in that type field will define what you see next. Here's the structure of the LTP header from RFC 5326, and it uses something that you might not be familiar with called SDNV, or self-delimiting numeric values. This is the idea that a field can be a variable length field, but we don't want to have a length field in front of it. So it's wasteful to say, oh, the session ID will be 4. So we don't want a session ID length and then the session ID field. Instead, we use this SDNV format, which basically says that the most significant bit of the last byte will indicate when we've hit the end of the field. So here's an example of a 2-byte field. If this field is defined as an SDNV format field, then we would look at the first or the most significant bit of each byte as we're reading the contents of this field. And when we see it begin with a 0, we know that this is the last byte of this field. So that's really interesting when you see these types of things. You know, we don't have an end of field delimiter. We don't have a field length fields or anything like that. Instead, we use this SDNV here. And you'll see this also in use in the bundle protocol. So this session ID value is variable length. Then we have the header extension count, which is set to nothing, and I don't have any trace files using header extensions or trailer extensions at this time. But if they are in use, they would follow underneath here where header extension is, and then trailer extensions would sit below the content for the segment itself. This is out of the same RFC, showing you simply the combination of possible type field values. So this is what Wireshark looks at to put that information up into the info column. It doesn't, however, provide you the full set of information all the time. You have to look inside the packet, and hopefully the dissector will be enhanced to show you a little bit more. But essentially, when we see a code 0 in this field, it indicates it's red data, but we're not at the checkpoint, and we're not at the end of the red part, and it's not the end of the block. So this is in the middle of the data stream, or the start of the data stream. And then we have one that is red data but a checkpoint, but it's not the end of the red part, and it's not the end of block. In other words, I just want to know, are you keeping up with what I'm sending to you? I need to get a report right now, see if you've received everything I've sent up to this point. So I will set the checkpoint, enable checkpoint. Code 2, we got red data. This one is checkpoint and the end of the red part, but it's not the end of the block. That means that green data must be coming up next. So we must have one of those blocks that has both red and green data, because we've got to the end of the red part, but there's more to come, so must be green. Then there's red data, checkpoint, end of red part, end of block. That's what we saw in the earlier packet just a moment ago. This just means I'm only sending red data, and this is the end of the block, and I need to get a report on this. Then we have green data, not end of block, and green data, end of block. There's our report segment is number 8. Report acknowledgement segments 9. These ones I don't have any examples of, the control segment stuff. We do have the ability to cancel communications. Either the sender can cancel the sending of a block, or the receiver can do that. There is a note on the bottom of here that explains, if you're going to use our Wireshark profile, you will note that we defined things based on this code number in decimal format until we got to number 13 and number 15. These two specific frame types for LTP communications, Wireshark won't throw a dissector on them no matter what we do. And that's because these are short. These are only 4 byte long. And Wireshark expects to see 5 bytes. So it's just this, it's a dissector thing. But so what we did was we did a different methodology in our, not only our coloring rules, but also in our buttons. And Ginny will show you that in the example of how we built our LTP Wireshark profile. So here are some of the different segment types that you would see. Okay, there's data segment. Contains the service data, metadata in it, whatever. There's your report segment that includes that claims section and the report serial number. Report ACK, which is correlated with the report using the report serial number. And then the idea that you can cancel a segment and cancel ACK. And going back, there are 2 different sides of canceling. Who's going to cancel, the sender or the receiver? They're each defined separately. So here's an example of a red data retransmission. If we lose a packet when we are sending red data only. Remember, we don't care if we lose a packet. When we're sending green data, there's no retransmission capability. All right, so we are in session number 2. We have just red data, sends at we send that down, bundle, we'll send it down to the LTP engine. The LTP engine will then send across. And let's say the first packet goes missing. Offset 0, length 200, that packet goes missing. Then the next packet is offset 201 with length 200. The next one is offset 401 with length 200. This is the end of the block. It's marked end of block. It's the end of the red part, and it's also a checkpoint, so it's asking for the report. The report comes back, and in the claims section it will say, I got from this offset right here, it will say I got offset 201 and I got 400 bytes. So essentially it's acknowledging from offset 201 to the end of the second packet here, which the end of the second packet would be offset 601. So this is acknowledging in this claim section this portion right here. That's an indication to the sender that we're going to have to retransmit that. The originator of this session will send back a report ACK segment, and they will be correlated based on the report serial number, and then it will send the missing segment, the missing piece. Now at this point, it's just marked as checkpoint. We can't mark this as end of block because the end of the block was up above. We've already sent the end of block. We aren't going to mark this as the end of the red part either down here because that was up here. What we will do is we will mark this with checkpoint saying, listen, we need to get a report back so we know you received this. Then we would see in the report, and what the report will do strangely is it won't say, hey, I got from offset 0 length 200. It will say, I got from offset 0 up to 601 in that claims section. And then you'll see the report ACK go across to say, great. But you'll see that we didn't pass up that data on the receiving end until we received all the contiguous bytes here. All right, so let's go take a look at a red data communication where we have a problem. We've got packet loss and we've got retransmission in it. The trace file is called LTP-red-1comb-issue.pcapng. So I've opened up this trace file, and here we can see that this is red data, and Wireshark is saying that it's reassembled all of this red data in frame number 108. Now we can just take the slide or move down to frame 108, and we can see here is, and let me just expand this, there we go. We are up to offset 127251 here. And we can see that this is red data. You'll see a checkpoint serial number in here because this packet is marked as a checkpoint packet. Remember that all of our trace files are annotated. So don't hesitate to look at the packet comments. Best way to look at packet comments in our trace files is to click down on the Capture File Properties button right next to the Expert button at the bottom, and in the top portion you'll see our section comment and our individual packet comments that are in here. So here we can see that frame number 108, which is going from .2 to .3, target port number is 3113. It's red data. It's the end of the block, the end of the red data, and it's requesting a report after that. Now here's where that checkpoint timer comes into play. This checkpoint packet has been sent across. It's asking for a report. There's no report coming across. The checkpoint timer expires. It sends the same packet again. These are checkpoint retransmissions that you're seeing in frame number 109, 110, 111, and 112. Those are checkpoint retransmissions. When we get down to frame number 113, there's the report coming back. Now we can look inside of this report and see what the reception claim is. This reception claim that we are seeing right here is saying, I want you to know I got from offset 127251 909 bytes. It only got one of these checkpoint packets. It did not get any of these previous data packets. That's what this is telling us. So it's telling us, that there's definitely a problem here. It sees the upper bound as 128160, which is what you get when you add offset 127,251 plus 909 bytes of data. But if this did receive everything up to this point, it would be offset 0 and length would be 128,160. That's not what happened. That means that everything that was sent across up to this point has to be resent again. All of these data packets have to be resent again. And sure enough, that's what we see taking place right after this. Here starts the retransmission. Now, in our custom profile for LTP analysis, we have a button up here for report and report ACK packets. And when you click on it, you can see there's the report we just saw. There's the acknowledgement for the report. And then in frame 223, we see another report, and this is where we see offset 0, length of 128,160. So everything except for that one packet had to be retransmitted in this trace file. Ugly. In the Wireshark challenge that Ginny's going to show you, you're going to see multiple reception claims where someone says, hey, I got from offset 0 to this, 1190. I got from this other offset to this one. You'll see a bunch of these reception claims coming up in that trace file. When you look at the CCSDS Blue Book, you're going to see the diagram that fits most closely to what I'm going to show you right now, which is the idea of a red and green a session, including red data and green data, sent as a single block to a target, and we're going to have a problem with this. So this is what you'll see in that blue book. It's very close to what I'm going to show you right here, which is where red data goes across, red data goes across, red data goes across, red data goes across. We have a checkpoint, end of red part here. Remember, now we've got red and green data, so we can't say end of block here. But we can say that we want a checkpoint and end of red part because we're about to go on to green. Anytime you say end of red part, you have to do it as checkpoint. But let's say that doesn't arrive at the target. We go on and we start sending the green part. So the green packets go across, but all of a sudden, one of the green packets doesn't make it across. All right, we're going to recover this red part data packet, and we're not going to recover the green part because green traffic is unreliable. So we have finally finished sending the whole block, and we can mark this as end of block here. We see the checkpoint timer must have expired for us to send another checkpoint out here. So we send the checkpoint out again saying, look, we got to get a report back. Did you get this up to the end of the red part? That gets sent across. We send the report segment back. And we get the report ACK coming back. Notice that it's the checkpoint timer that actually triggered the retransmission of this packet that never made it. It's not the report coming back and saying we have all these holes in the receipt here. It is the checkpoint timer that triggered this retransmission right here. So this is another way of data recovery for red data. And we will not go through the process of trying to recover the green data. So now is a great time to go over and check out the video that Ginny has on how to create the Wireshark profile that we use for our LTP analysis. It will help so much when you're analyzing LTP communications. And then also go check the Wireshark challenge that Ginny put out to let you go ahead and test your knowledge of analyzing LTP traffic.